Of last time. So essentially, we were looking at transport from a ballistic regime to diffusive. Hi, Howard. And ballistic is defined by length scales when the elastic length is much bigger than all the physical lengths of the system. And diffusive is when it's in the opposite regime. In between, it can go through some quasi ballistic and so on. And we were looking at a 2D gas. So if you remember, there was a little confusion about A and W, but really that was okay because we were looking at taking a 2D gas and squeezing it. And so we were trying to go from a conductance which we derived to be E square over H, spin 2, the number of modes in the channel, which is basically W over lambda F, and T was the transmission coefficient. And what we showed was that the transmission coefficient does not go exponentially in L, but more or less 1 over L because of the repeated reflections. And then we basically got the T became a 1 over L, and we got this Ohm's law in the diffusive limit. And then we looked very briefly, I discussed this quantum corrections, and I don't want to go into it in detail, except because today we are going to encounter another log-dependent conductivity. I want to bring this up here. What I said, I didn't do any of the derivations, but what I said is very close to the Ohm limit right here, where we are going to put in the first quantum corrections. They show up as a transmission. You're trying to go from here to here, so there's a transmission you're looking for, but in between as the electron is transmitting, it gets caught up in some kind of a, you can think of the wave trying to transmit, but it then scatters off multiply, many scattering centers along two different time reverse paths that are equal. Okay, so the interference along these two paths is constructive, and that means it takes away from the transmission. So the transmission is less than what it would be because of this constructive interference between the two paths, which leads to localization effects. So your conductivity is reduced by some amount, and that correction is dependent on how long a path, you can sustain phase coherence. And that length is essentially coming from the inelastic length, which is temperature dependent. So that's how you get a temperature dependence here, which basically says that if you are looking at the resistance, there's some phonon scattering and what have you, and it's come down, it's saturated, it's now just coming from impurities, and then at very low temperatures, some localization starts happening, and the resistance starts going up logarithmically in temperature.
So even if the converse effect doesn't happen, I mean, we're saying that quantum interference is now appreciable, so why can't you have destructive interference, which means that you're more probable to transmit?
It depends. If you put in, so you're looking at e to the I theta, and then plus another e to the minus I theta. So that comes in, because the thetas are identical, you get constructive interference. You can get destructive. Let's say if you had something which would flip the phase of one of the branches, like magnetic fields and so on, can destroy this interference. So now you can also see that what was a log correction can start getting reduced because of magnetic fields, which can destroy this interference.
I see.
But left to itself, just pure impurity scattering, no magnetic anything, will produce constructive interference between the two time reverse paths, and that means the electron wave is starting to live more in some region, right? So the transmission is getting less. So this was the effect, and we got a log correction at low T. Any other questions on this? Because with this, I'm now sort of moving into spin today. And spin will play a role in the rest of our discussions. Did anyone have any other discussion? Any other question? Okay. Okay, so today what I want to tell you about is Kondo effect, and I want to do it in a few parts. Hi, Michael. I want to do it in a few parts. First, I want to start with this effect has been known for a very long time. So I want to give you some dates on this because it's rather remarkable that we are in 2010 and we are still discussing this. So 1930s, I won't give you exact dates, just roughly. This is when the first experiments were done. First experiments. And let me tell you what these experiments were. So they were essentially looking at, it's amazing how much we squeeze out of just resistance versus temperature. It's like we need to move on, but we get trapped in these whirlpools. So here is again resistance versus temperature of very simple metals. Metal, for example, copper. Okay. Now, what it's doing is, as we keep drawing, there's some finite temperature part, T to the 5th, from phonons. Then you reach a temperature of order theta debye, right? Now the phonons don't play a role. It has become flat, but then suddenly at low temperatures, this resistance started rising, like that plot. But here it doesn't have anything to do with quantum corrections. And, okay, so it started rising at low T. And initially it was not known what the cause was because people thought this was pure copper, but it was soon, I'm going to cut the chase a bit, it was realized that copper had copper with magnetic impurities. For example, iron, cobalt, etc. Very, very tiny concentrations. Tiny concentrations. Because in fact, they were trying to not even look at impurities. They were trying to look at pure stuff, but it's the 30s and they can't make it so pure, so they had some, inevitably they had some impurities, and that caused this rise. So that's kind of the first experiments, and this temperature, so it had this sort of minimum. Let me sort of exaggerate the minimum, like this. So this temperature here, sorry, to make this better. So it's kind of between this and theta debye. This is another temperature scale we will define in a little bit. But this is another scale, the minimum, and then it starts going on up. And what was noticed is just a few things, that T minimum, which we are defining as some Tk, and I'll tell you the reason for K. K has to do with Kondo, but I will get to that. Basically went like an impurity to some 1/5 power. Some funny power. And that power will be related to this T to the 5. But it went to this 1/5 power. And our minimum was also related to n impurity. So these were just empirical observations in the 30s. And believe it or not, it took 30 years to get the first explanation of this. So actually that date is sort of 1964, Jun Kondo first gave an explanation. Within perturbation theory. Okay, and I'm going to go through some of the key ideas of that perturbation theory, but let me just summarize the result first. What he showed was that essentially the effect happened because of a perturbation H prime, which was of the form Js dot S. This is the spin of electrons in the conduction, in the metal, in this case copper. And big S is the magnetic moment of the impurity. This is the impurity magnetic moment. So you have some magnetic moment. Here is that iron or cobalt, and there are all these conduction electrons. This is from the C, the copper C. And between them, there is some interaction. And because of this interaction, essentially what happens is an electron in the copper C is scattered by this impurity. And just like calculating resistivity due to scattering, and I'm going to details on that, but scattering kind of analysis then can give us a resistance. He did perturbation in this G. He found that the would be a transition of, and when you look at mod square, like J square, direction he went with, and he got log. I'm going to tell you a little bit where he got it. Sorry, it's getting skewed here. So rho was shown to be, rho went like plus JQ, the next step. Let me write it like this. 1 plus J log E. So he gives the functional form. There's a log T dependence. T is a temperature scale. Unit is huge on this scale. So T is much smaller. So you basically get a this one is uncontrolled at 0 temperature. This term takes over this term. So perturbation theory was not, okay, so he gives some explanation. Resistance to a constant. From here is temperature, some impurity kind of independent. But then because of this, it starts to go up long. Then the electron breaks down to go up to become arbitrarily. So this is where stopped. And I'll just give you the rest of the history, come back to this analysis. So now what is going is that, first of all, experiment, right? Resistance. Which is log. People found it takes so many years to even the argument. Then it turns out theory and technology of the phenomenon. And it's really okay. This could have such, but the was so that was kind of 60s, 1960s. How to fix divergence of rho infinity at to 0. How to fix that? And Bill Anderson, whom you've heard of, and he called it poor man's scaling. And it was a quick way of understanding some kind of a renormalization group idea, but it was more qualitative. And then in the 1980s, we have a more exact solution by Ken Wilson called numerical renormalization group. NRG, and this is Ken Wilson, and he got the Nobel Prize for this. And then also in the late 1980s, I don't remember the dates, we have an exact solution. So this was a numerical one, but then we have an exact solution by beta ansatz techniques. And this is by Nathan Andre. in the US, and Paul Wiegmann, who's now in the US, but at that time he was in Russia. Paul Wiegmann. Okay, so that's kind of the history. But this, I wanted just to throw these words out. We are not going to discuss any of these highfalutin techniques, but just so you can see, here is a simple looking problem. How hard can it be? We have copper, which is a non-interacting metal pretty much. And we put one impurity in that, a single magnetic impurity. And we need a whole arsenal of techniques to solve that problem. You know, what hope do we have for things like cuprates? So, yeah, but that's the situation. So now what I'm going to do is go back to this perturbation theory, because even though it's not exact, it gives you quite a lot of insight, much more than we can get from these techniques, even if they are exact. So, okay, so actually let me say one more thing. So, you know, then you might say, okay, things ended in the 80s. So what are we doing now? We are still 30 years from that time. And the point about that is, these certain predictions were made from these theories, not just about the resistivity, which of course was verified, but also about structures in the density of states. That was never seen in any of these bulk materials. And that's called the Kondo resonance. So I'm going to describe that. It's a very sharp feature seen in the density of states. And it essentially says that if you were to look at the density of states of copper, so let's show that here. So not only one hallmark is this resistance minimum, so this is one hallmark. The second hallmark is something called a Kondo resonance, which is essentially a peak in the density of states at EF. So let's say if I just look at some density of states of copper, right, it has some square root of E feature like this, but then at EF, there is a very sharp feature. This is the Kondo resonance. This was a prediction actually by Abrikosov and Soule. I'm not writing down those names, but they basically predicted that the density of states will have this huge pileup at EF. It's a very dramatic feature. It was never really verified in any of the bulk experiments because this feature is very tiny, the width is very small, and it's on the order of this Tk. So this width is on the order of Tk. So the same temperature scale shows up here. And Tk is about 10 Kelvin. So Tk is about 1 to 10 Kelvin. So this Tk is approximately 1 to 10 Kelvin. So it was never really verified. So the beauty of the quantum dots is that you can tune many things in this Hamiltonian, and you can essentially probe this density of states. As you know, we have been looking at these IV characteristics, and from that we can look at the density of states in tunneling, and that becomes a perfect way to probe the dots and look for these features. So that's what brings us now to 2010, like say the 2000, when people started making quantum dots to probe the Kondo resonance. So the effort kind of moved from gross properties like resistance as a function of temperature to more specific features in the spectral function or the density of states. Okay, so let's just try and get some handle on the perturbation theory. Okay, so qualitative to write down some kind of a perturbation Hamiltonian H prime, and this is often called the SD model. Often called the SD model. Where S is just the conduction electrons, wideband. So this is our so-called copper, for example. Copper. We know copper has D bands, but that's really not playing a role. It's just some generic metal. So this would be like a parabolic wideband. And D is the localized impurity. Localized D shell or impurity. For example, cobalt. Okay, so a Hamiltonian that one can write for this is of this kind. This is the perturbation. HSD would be times. Actually, let me write it in pictures. It's actually easier to understand the processes in pictures. So what happens is you have an electron, and we're not going to go through a whole lot of diagrammatic analysis, but the pictures are pretty useful to see how these processes come about. So you have an electron. After all, in transport, we are looking at an electron from K scattering into K prime. It's the same kind of process. Electron with spin up scatters into an electron with spin up with the momentum changing. This would be one of the processes we have looked at before. And it just takes this impurity spin and goes into the impurity spin with the same unchanged spin direction. Okay, so this would just be like a non-magnetic scattering. So there is a process of this kind sitting there. A similar thing with down spins, which I'm not writing. Similarly, switch up to down. No, I shouldn't say switch because there's a spin flip I want to introduce. So I don't want you to confuse it. Similarly for down spins. Okay, but the more interesting ones are processes of this kind, where you have K up, let's say, going to K prime down. Yeah, I have it wrong here. K prime down, and yeah, and a down spin goes into up. Okay. So basically what it is saying is that if I had to write down a Hamiltonian for this, we would get something like this. If I have to write it out. So this is a kind of process where the electron spin, not only is the momentum scattered, but the spin is also flipped. So this is a spin flip process. Okay, and we can write these terms as, so let me continue here. So you can get terms of this kind. Let's say AK prime So I is the position of the impurity. So you're getting a little flavor. I want to give you a little flavor for, the next kind of theories one will start to invoke. So let's see. I'm going to explain this very carefully. This one is basically one term of these two. One of them, the up one, I have shown here. Because what you see is that the electron goes from, you destroy an up, K, you go to a K prime up, and this is just coupling to the Z component of the spin, which doesn't change. Okay, and you can have another one like this of the down type. This one says you can either raise the spin operator, so you can make a down go to up, which is the picture I've shown. You can also have a reverse one where the big spin, the impurity spin, up goes into down, in which case it's a spin lowering operator. Okay? And along with that, the electrons do the opposite. Here, a down electron becomes up, and correspondingly, the impurity spin is lowered. Here, the up electron becomes down, and correspondingly, the impurity spin is raised. Is that clear? Okay, so that's the kind of Hamiltonian one would write down. And then, once you have, yeah, question?
So, I get the spinning, how the spins work, but what about the momentum? Does the momentum just get absorbed by the, so you've got a change in momentum, right? So where does that go? Does it just get absorbed by the ball?
Yeah, it's like an impurity, right? So it's elastic scattering.
Okay.
And it's like hitting a wall, and a ball comes in, it can change its momentum.
Okay.
It's like you
So just in direction?
Just in direction, yes. So it's elastic scattering. I should have, finally, when I look at the transition matrix element, I will have energy conserving delta function. So now I want to go from W, A to B, so K to K prime. So let me just write it as some initial state to some final state. And we would have something like 2 pi, this is the golden rule argument, delta EA minus EB. So I'm doing elastic scattering. Times we would have something like A HSD, it would take us to B and then back again. B HSD A. Okay, that's one term, that's first order. But then we would have another term which would basically be of the form, let me just write it. So you would have another intermediate state, and then you would get an energy denominator. So you would go A to C, C to B, and then B to A. So A, HSD, C, HSD, B, and then B. And then this would involve the energy of the intermediate state. Okay. So this is the next step. Okay. And what turns out is that the first term is just like this, is similar to impurity scattering, similar to non-magnetic impurity scattering. And in this, there are many processes, like we can write down. This can go do that, etc. But there are some terms which are what are called singular, meaning they have some kind of a log divergence. And that's all we need to concentrate on. Anything else which is constant or more weak singularities, we don't need to worry about. But sitting in this term is there is a singular piece. This term has a singular piece, and I'll show you where it is.
On the first term, why do you say it's similar to non-magnetic scattering? We have all these spin flip events in our Hamiltonian.
Yeah, but it is, you want to go, say, from, so let me just draw that. So you'll see, because I'm going from A to B, and I'm not able to, I have to come back to A. So this, okay, let me just draw that. It's a little bit easier to see. I want the intermediate state, so I need 3 states to generate that singularity. Let me, unfortunately, the board space isn't much, so I'm going to erase and then. Okay, so let me just draw one singular term, and then you will, one term from the second piece. So it'll be something like this. You have an intermediate state and then you scatter, because now you see in the matrix, in the transition probability, I want to invoke one intermediate state. So let me say this is a K up, this is, let's say, a Q down, and that's a K prime up. And each time there is some impurity, there is some magnetic impurity which does something. So here, I'm going to go like this. Basically a down, since the electron flipped down, the impurity must flip up. So the impurity down must flip up. And then it must flip down in the second process. Okay. Now let's come to Andy's question. Okay, so this kind of a term will have, if I look at this term in all of these, from that, from this second piece here, because it has a denominator, it generates singularities when you have to do some integrals. So a term like this will have a contribution. This has a contribution that goes like, there are many pieces, this has to be occupied, this has to be occupied, all of that is there, but basically Q must be unoccupied. This must be some unoccupied state. So it should go like 1 minus some f of Q over Ek minus Eq, summed over all Q. Okay, now you can see that if I looked at any term here that Andy was asking, say I just went from A to B with a spin flip, and I don't get these denominators, I can still integrate it all out and I will get some constant. It's because the second term brings in this denominator. When I try to do this integral, and I'm not going to do that here, it's very easy to do this. You get some, it's in 3D. So you will get some weight from here, which is dq, q squared dq. You have something here. When you do the whole integral, what you will get is a term like this. This you can show will go like a constant plus k over kf. Kf because I'm going to allow these k's to be only around kf. Okay, I'm looking at the electrons in copper are basically at kf, and then they are scattering around the Fermi energy. So it's k over kf log log k minus kf over k plus kf. Okay. And so you get this log divergence. If you want, I can show you where the log is sitting there. But if you want, you could try it, and then I can show you how we do these log things. So try it a bit. It's kind of simple. You can just expand this, and then this will be take everything to be just parabolic. So ek is just k square, eq is q square, and then you just do this integral over dq q, and you'll see there's a log sitting there. Okay, so you get this log correction, and that is basically the origin of this log singularity. Now, where the temperature dependence comes in is from f of q. So if you now, I did this at 0 temperature, if you now want to go back and put in the temperature from f of q, that then leads to, so now temperature dependence from f of q, and that then gives us rho resistivity. Which basically goes like W K prime, summed over all. So it's basically W K prime summed over all K prime, and delta EF. So it's basically all at Fermi energy. So from that, we would get something that does J squared 1 plus log EF over T. Okay, I've just sketched it. I haven't gone through all the details because it's not that useful. It'll just take up a lot of algebra. But I wanted to just give you a flavor for what is involved. So what is involved is there's a magnetic impurity, single magnetic impurity, and that couples to the conduction electrons. That coupling is essentially a J little s dot big S, which is shown by these pictures. Because little s is the spin of the electron in the conduction band, big S is the impurity spin. And they can exchange just in the Z component. That's not so interesting. But when they spin flip, that's the important one. And you have to go to higher order in perturbation theory than we have been going in order to get a denominator. Okay, it's only when you go to second order that you get a denominator, because that involves the intermediate state. So when we did impurity scattering, we stopped here. And we got some, when we derived our Drude formula, we stopped here. And then we got some K prime mod square, and that was some tau, and that was the end of the matter here. Now we go to one more term. From the energy denominator, just this integral gives us a log. And if you put the right temperature cutoffs, you get a log EF over T. Okay, so those are the key ideas for where the singularity was hidden and how it got exposed by going one order higher in perturbation theory. And this is basically Kondo's solution, or Kondo's result. Okay? So it stops here where it says that the resistivity has this log term, but then it doesn't resolve the behavior at very low T. And that's where these other methods come in. And even though I won't go into what those methods, how they work, let me give you the result, which is really very intuitive. So what they say, these more fancy RG methods, essentially give the following result. Here is resistivity, here is temperature. It's coming down, it minimizes and then goes up and then saturates. This is the result of all of those RG methods. Okay, so here is TK. So this number here is saturated. So rho tends to something like 2e squared over h, or rather, no, that's sigma, that's g, so I'll come to that. But basically, a rho tends to saturate some. This comes out of from scaling theory. Let me just say scaling theory, because I have never really studied the RG methods, but Anderson's scaling theory I have. It's a very beautiful theory. It's almost quite easily teachable in like the next many-body course. So just from that, you can show that if you go to low temperatures, the resistance becomes constant, and the picture is very intuitive. What the picture is the following. What is the picture is that you have this impurity spin. This is the impurity spin. It essentially, so there's a Hamiltonian, this JHSD, which is nothing but J little s dot big S, and this Hamiltonian essentially forces the two spins to become antiferromagnetically aligned. J is positive. J is positive. So it forces the two spins, so this and the conduction. So it's not a single electron that is forming this singlet. It's kind of a many-body cloud, which is what makes this problem complicated. But nevertheless, for our purposes, it is a singlet. So here is my, here is my cloud. And let me denote a little spin here as the collective, some kind of a variable for the cloud. And the impurity spin and conduction electrons form a singlet. Okay, now what does a singlet mean? A singlet means a state of this kind, up, down, minus, down, up. Okay. Here is the impurity, this is the conduction electron. That's the impurity, and that's the conduction electron. Okay, so it's an entangled state. It's a coherent superposition of both of this. So it's an entangled state. It's a many-body, I should say it's a many-body entangled state of, by many-body I mean it's these many electrons. So I will maybe come back to this again towards the end, but here's what I mean by many-body. We started out with all these electrons in copper which are not interacting, right? So there's no many-body stuff there. It's just a single levels Fermi statistics. So there's no interaction in the copper itself. The impurity interacts with, let's say, one conduction electron, but then it interacts multiple times with many other conduction electrons. So even though they were not interacting with each other, because of the impurity, it generates some kind of a coherence among the conduction electrons and the impurity. And so that cloud, this singlet is not just two electrons forming a singlet. That would have been a two-body problem. But it somehow involves this collective object. Okay. Now, what is nice about the quantum dots is they are trying to image this Kondo cloud. They have not succeeded yet. But that's kind of the development one can foresee in the next 5 years, I should say.
So this coherence between the conduction electrons decays over some length scale?
It decays over some length scale, which is the size of the Kondo cloud,
right.
And it has not been imaged. But it's a big cloud. It's not a tiny two-body, small singlet. It's a big cloud. And it's of order, once you have an energy scale Tk, you can construct a length scale. So basically h bar square over mLc square is Tk. You can write something like, so what is the size of the Kondo cloud? Everything will now be called Kondo resonance, Kondo cloud, Kondo temperature. We just associate all of this, of the Kondo cloud. Kondo singlet cloud. And basically you can say that if you have an energy scale Tk, h bar squared over mc square has to be on the order of Tk. And so that defines C. Okay? So this part is a bit in words because that's all we can do. We can't penetrate that part of the literature. But the point of it is, once the system has become a singlet, the spin is gone because the spin of a singlet is 0. So we started out with an S equals half impurity. By forming a singlet, that spin is gone. So the system now, below some temperature, basically looks like non-magnetic impurities. Where the non-magnetic impurities is basically the concentration of these cobalt ions. So it essentially then levels off at a resistivity which is related to any square tau over m, but tau kind of coming from scattering off of these now they have become non-magnetic impurities. Okay? That is the picture.
Why do you have to go to low temperature to begin with to see the scattering off the
You have to go to low temperatures to form the cloud. Because what you have is this impurity scattering. So the electron scatters off one impurity. Then another electron comes and scatters off that same impurity. That generates a coherence in the scattered electrons. Okay, coherence basically means you're retaining phase information. Right? That's what coherence means. One scattering, another scattering, you keep that phase information. So you have to be at low temperatures to get that. So that's why below Tk, you're starting to form the Kondo cloud. And then at kind of, there's a rollover, and basically when you go to low enough temperatures, the Kondo cloud formation is complete. Now it is a singlet, and then you get this resistivity just determined by impurities. Is that clear? How would you want to say something?
Oh, I buy it.
You buy it.
I know. I wrote paper on
You shouldn't buy it so easily, even if you wrote a paper on it.
Why is the formation of the Kondo cloud giving rise to the increasement of resistivity?
Let me back up a bit. So the increase of resistivity, let's write down a few things. Increase of resistivity is due to spin flip scattering, let's say. Okay? So the Kondo cloud hasn't formed yet. This is, at very high temperatures, the electrons are mainly getting scattered by phonons. Then at some low temperature, phonons are now not operating. Now another mechanism starts operating. So the electron comes in with momentum k, scatters with k prime. That scattering is what is leading to an enhancement of resistivity, especially when that scattering is involving a spin flip of the electron. So you come up with an upspin. This should have a director here. So something like this. You know, you have an upspin, and because of an impurity scattering, it goes down that way. That process leads to this enhancement. Okay? Now, somewhere around here, so it's on the same scale, right? We don't get multiple scales. So it's maybe like tau tk by some factor, 5 or something. That's when, because of multiple scattering, now the Kondo cloud, which means the singlet, has formed. Okay? So within the Hamiltonian picture we wrote down, we could only look at scattering processes. But in a way, what you're saying is, suppose that was my Hamiltonian, and I could solve for the exact ground state. Right? I'm not trying to treat one term as a perturbation. I have been given a term which is the copper term, k square over 2m, and another term which is this hsd, and I want the ground state. Then in the ground, so now I want to just look at the behavior at 0 temperature. That's when I can talk about a ground state. What is the ground state? And in the ground state, the RG solution says that these two, the impurity spin and the cloud, have basically formed a singlet. So now the way to think about it is a picture like this. Here is my impurity, right? There is a cloud which has formed a singlet, and it has some length scale. So this is the singlet. Now you want to look at scattering from this object of another electron, k prime. Right? So what I'm trying to say is that previously I was looking at the scattering of an electron from this impurity, this magnetic impurity. Now, because of the cloud, I have a composite object. That composite object is just like a non-magnetic impurity because it has a total spin equal to 0. It's a singlet. So now another electron which comes in sees a singlet, right? And it says, that's a non-magnetic impurity. It scatters off that and just gives you a constant resistivity. Yeah.
So the conduction electron that forms the singlet, is it a free electron or somehow?
It's a free electron, but it has now become, it started out as a free electron. Now it has become some kind of a bound state with the impurity.
So
and
it is somehow localized?
Well, it is localized. Well, okay, yeah, if you fix the position of the impurity, it will be localized. So usually in these metals, they are roaming around. So it's a dynamical bound state. But let's say in a quantum dot, you could localize the big spin, the cloud would then be localized. It has to be.
Well, in a bulk material, is that the D state localized?
No. You mean this spin?
Yeah.
This spin is on a D shell in cobalt, and it is much more localized. So it is a local moment, yeah. But that local moment, it depends. In the metal story that I told you earlier, you had a finite concentration of these impurities which were running around, and then this cloud is a dynamical cloud, right? It forms around that impurity. But let's say in the quantum dots, which I'll come to, it will be formed, let's wait for the quantum dot story, and I'll tell you where it exists. But you know, the reason this is hard, it's not just this picture, is all these electrons are identical. You know, it's not like this electron is on the dot, and this electron is, or rather this electron, the electron on the impurity is the same object as an electron in the conduction band. They are all identical, just fermions. So that is the reason why, when I say this has formed a cloud, these electrons here are the same as there. So they are also exchanging. So I don't want to say too much because the more words you use, it gets more confusing. But at least I think qualitatively, this is the picture. I want to be sure you all understand it at some level. This one, which shows, so here, singlets, the second step is increase of resistivity is due to spin flip scattering, and the second point is resistivity saturation. Because a condo singlet forms between you write that here. So here, second point is from here. Resistivity saturation, because a condo singlet forms between impurity, big spin, and conduction electron. And when I say up or down, they are arbitrary, right? You have singlet, it's up, down, minus, down, up. So it is up, down, minus, down, up. And this is the psi condo, so to say. And this has S, total S, total S, total S equal to 0, which now implies electrons now scatter, effectively scatter off. Non-magnetic impurity, and that implies rho tends to constant as T tends to 0. Okay, so that's the phenomenology here. So that's kind of where we stopped around 1980. And then came quantum dots, which allowed much more testing of these Hamiltonians. Because in a typical, previously, you were given a cobalt spin. You could not change too many things. You could not change its coupling to the conduction electrons. You could not change the type of impurity. So now you could do much more of all this tuning, and now it allows us to, yeah, question?
What limits the size of the condo cloud? Seems as you reach lower and lower temperatures. Coherence can get
You're
longer.
saying why does it not?
Why would it not be the size of the entire sample?
Okay, so let's wait a bit and I'll tell you what limits Tk, the condo temperature, and that will tell you then what limits the size. Okay, and it becomes more clear when we do dots, because there you can actually change some of these parameters. So let's come to that. review a very little thing about dots. And, no, let me see, do I want to do that? No. Let me start out like this. So let's say I have, this is my tunneling barrier. Here is my lead. This is the source. This is the other lead. This is my lead, the second one, which we also call the drain. And you should think of these leads as our copper, the metal. Okay? So these leads are like our copper, and this little thing here is the dot. This stuff here is the quantum dot, in which we can have, let's say, a state somewhere here. So here is some state at an energy, let's say E0, measured from here. And these are almost at chemical potential. So I can just move it a bit to measure conductance. Okay. Now let's say, so this is my dot, and the quantum dot is like the big spin. That's like the impurity spin. So now, how does the whole thing play out? What you have is, let's say, a spin on the dot. Let's say I have an up spin here. So what it's going to try to do is to form a singlet with an electron in the conduction band. So, right? So the first thing to notice is that this is the chemical potential. This is EF. If this spin was above EF, right, it could just have moved into the leads and vanished. It'll just decay, right? If it's below EF, it typically cannot tunnel because there's a barrier. But it is interacting with some environment, so this level is not a sharp level. I'm showing it as a sharp level, but forget any Kondo physics. Just in, when you do quantum mechanics and you look at some eigenvalue problem, these are all absolutely sharp. They are eigenvalues. If you have a coupling with some environment, then those eigenvalues take on a width. Right? So this electron is kind of tunneling, it's trying to tunnel to other available levels, and that is the environment that this blue electron is coupled to. So there is a natural width to this level. Let me just say, I will draw it here. Some width, gamma. So, because the spin on the dot, or the electron on the dot, is coupled to the leads, there is a finite width. Width to the level E0. And that's just a normal broadening. So that's, so if I try to look at any tunnel conductance, it will be broadened by this amount gamma. Okay, that's just for any tunneling into any level. But now we are going to look at the actual process. So for a quantum dot, there are various energies, right? If I have a dot like this, there are various energies. One is because of size quantization, there is a delta E, which goes like 1 over r squared. This is just size quantization. But the more dominant energy, so this is one. The second, which dominates, is what? Yes, Coulomb. Dominate. Second is charging energy, which we discussed before. EC, which is E squared over 2C. And C goes like R. Okay, and EC is actually bigger than delta E in the dots I'm concerned with. You can go into regimes where you're in the other limit if you make a very big dot. But for the small dots, this is for small dots. The dominating energy is the Coulomb energy. Okay, so now let's see how that works. So basically, I want another electron to hop on this, as it is trying to exchange with this. So,
Real quick,
yeah, question?
if delta E goes as 1 over r squared and EC goes as 1 over r, for small dots.
Yeah, actually, I should say for some intermediate dot.
Okay.
For some intermediate. I don't mean the very tiny dots, yeah. So here's what I mean. If you had a very big dot, basically Coulomb will not be important. That's our metals that we have been looking at. That's the regime of a very big dot. And then Coulomb is not important. Then you start squeezing at some point, but Coulomb becomes dominating over the kinetic energy. No, dominates over, so actually I should draw it here. Here is R. Very large R, kinetic energy is much, much greater than Coulomb. So let's say Coulomb potential. At some point here, potential energy is becoming dominating over kinetic, like we talked about, this Wigner crystal story. If you go to even smaller dots, even smaller, then size quantization takes up. So I'm kind of in this regime where potential energy dominates, but the size quantization. So actually what I want to say is that yeah. So delta E is some scale like this, which is coming from size quantization. And if the dot is a certain size, you have some level spacing, but yet if I have one electron there, and I try to add another electron, this is a single electron picture. I have to look at now the energy of n and n plus 1. That is different by E squared by EC, which is a much bigger scale than the little scale that was coming from size quantization. Okay, that's what I mean. Okay, so now coming back to this picture. Okay, I have 5 minutes. Let's do this and then we'll pick up again. So what you have is you go you're starting out with this. Here is, let's say, a down electron with which it is trying to make a singlet. This is my initial state. So the electron now a second electron hops on this. So here is 0. So this is a virtual state. It's an intermediate state. And this is the final state, in which I'm going to have a spin flip, where okay, so what happens is the dot up electron is interacting with the conduction electrons in the lead. Okay, and basically the spin flip that I talked about is going to have this kind of a form. It's going to go through an intermediate state where this electron hops on that site. And of course you could have had one situation where the red hopped here and the red hopped out there. That's like one of the terms in the Hamiltonian which did not involve a spin flip. And those are the non-singular terms. But the singular one is when this hops here, that intermediate state now has an energy of order u, and then it hops over after a spin flip. And this process gives rise, so there's a paper by Haldane that calculates Tk for such a geometry, and he finds that Tk is now equal to half gamma u. Gamma is the natural width of that E0 level, just because it is interacting with an environment. So gamma u to the power half e to the pi E0 some expression. And I haven't really looked at that paper to derive it, but I could if I get really excited about it. But for now, I'll tell you the main experiment and then we will come back to this. So the key point about the quantum dot is the following. So this tells you why quantum dots are so useful. Why quantum dots? Because remember, we have a gate. This was the geometry of our system. We had a source, a drain, and we had this gate, which allowed us to shift that level E0. Okay, now the beauty of that comes through, because the gate can move that level E0 anywhere I want. So clearly, if E0 is very low down, it's going to be barely coupled to the leads. Gamma will be very tiny. As I bring E0 closer to the Fermi energy, it's going to get a larger width because the coupling to the leads will increase. Okay? Now I can change the size of the dot, and I can change u. So there are many parameters you can vary. So essentially, use the gate to vary gamma and E0 position. And then change, again, use gate. Remember, these dots are not physical round dots. They are made by putting these gates. So the dot is basically defined. It's like a shape, right? It's a shape which is defined by the gates. So the same gates can also change U. Okay, so we have tremendous control. You can change gamma, U, E0. All of them.
Why does it adjust U? Because it's like KQ over R?
Yeah. So it's E square over C. By U I mean, sorry, this is U, or you can call it E square
That's
over
the
C.
charging energy.
It's the charging energy. You can also call this EC. Yeah, I think of it as U, but it can also be called, so EC and U are the same thing in my language. Okay, so you can change both. And now comes the interesting part. What I'm going to show you next time is that all the resistance data will change. You know, as you change U, you change gamma, etc. But if you scale everything with TK, this single energy scale, everything will collapse on the same data set. Okay, so in other words, we will look at the conduction through such a quantum dot next time, and we will see that depending on where the gate is, there's a certain resistance. As you change the gate, the resistance is different. But if you scale all the data, by scale meaning you replot it in some terms of a temperature divided by Tk, everything will collapse on the same curve. And that's what these plots are. So bring it with you next time, tomorrow, and then we will basically discuss this experiment. Do you have any questions as you leave? Or maybe bring it with you tomorrow, and then we